So in this problem, I'm asked to solve a reciprocal trig equation. These are reciprocal, let me get my pen going here. These are reciprocal trig functions. And that's going to have some implications in terms of domain restrictions that we'll get into later on. But the first thing I noticed looking at it is not only are there reciprocals, but there are different trig functions here. Tangent squareds and secant squareds. So that means greatest common factors is not going to work. I'm going to run into trouble if I try to factor a trinomial here. In fact, anything you do short of an identity substitution is just not going to work. We need to make identity substitutions to finish out, or to even get started on this equation. And then it comes down to which of these 9 most common trig identities do I use? Well, I'll just point out that none of these angles are double angles. Now, that doesn't mean you can't use double angle identities, but it means maybe we should try something else first, okay? It's a hint, it's a guideline. So the next thing I might try is either quotient identities or Pythagorean identities. And simply because there are squared terms, there are squared exponents, that's a hint that maybe we should use Pythagorean. So let's go ahead and get started with that. Pythagorean identity I want is, let's see, we've got secants and tangents, so I think the tan secretary is going to help us out here. 1 plus tangent squared equals secant squared is the identity I'm using. So we make that substitution. Everywhere I see a tangent in this equation, I'm going to change it. And the reason I'm picking on tangent is because there's only one of those, and it's squared. Whereas if I picked on secant squared, this one would change fine, but I'd have a lot of trouble changing secant if it doesn't have a squared on it, right? That's not going to turn out well. There's going to be ugly square roots and things. So secant squared plus 2 secants equals, well, what do we get here? What's tangent squared? That is secant squared minus 1. Okay? And now we can just combine some terms. I have a secant squared on the left, a secant squared on the right. Those are going to cancel out. This is going to simplify pretty fast, actually. So I get 2 secant equals negative 1. Okay? That means secant of omega equals negative 1/2. And I don't know my secants very well, but I do know that using a quotient identity or a reciprocal identity, I can change this into cosine. And we're going to flip this over. So negative 2 over 1, which is just negative 2, which is a problem because cosine has to be between negative 1 and positive 1. You can't have negative 2. So there's a quick answer to this one. It's a big old DNE. It won't always be DNEs. DNEs are actually kind of rare, but this one is an extraneous example. Now, I think I said there were 2 ways to solve this. One is by jumping right into a Pythagorean identity. Another is, what if we go for a reciprocal identity or a quotient identity first? Well, to do that, let's write the equation this way. And I'm going over both because really it's just a matter of what ideas you come up with to try. And there are many right ways to get to the answer. So I want to do it this way. I'm going to change all the secants to 1 over cosine. So here we have 2 over cosine. And here we have sine squared over cosine. Remember, that's tangent squared. And now we're going to multiply this whole thing, both sides, by cosine squared omega. So what do we get? Those cross out, we get 1 plus, this crosses out, and we still have a cosine left over, so that's 1 plus 2 cosine omega equals, and these cross out, giving us sine squared omega. And now we can make a sine squared substitution using the Santa Claus identity. Okay, so that's going to be equal to 1 minus cosine squared omega. And here we still have 1 plus 2 cosine. So move some things around. I want cosine squared on the left, so it's positive. And that's going to be cosine squared plus 2 cosine equals 0. The 1's canceled out. So this becomes cosine of omega. That's my GCF. And cosine omega plus 2 equals 0. So we get 2 possibilities here. One is that cosine omega equals negative 2. Well, that does not work. Okay, that's extraneous. Because you cannot have a cosine value greater than 1 or less than -1. We've already talked about that. The other possibility is that cosine omega equals 0. Well, that doesn't look bad. That tells us that omega equals pi over 2 and 3 pi over 2. Remember, our unit circle values where the x-coordinate is 0. Those are right here, top and bottom. So I think that's okay. We have to check domain restrictions, and that's especially important when you have reciprocal equations. See, this reciprocal equation was loaded with secants and tangents, and those all have cosine on the bottom. Now, if you remember your domain restrictions are the following. Secant, for secant theta, you cannot have pi over 2 or 3 pi over 2, and that's exactly what we do have. And likewise for tangent. Okay, tangent omega has the same domain restrictions, because on the unit circle, those are actually D and E spots. Those are like the one angle you cannot have with a tangent or a secant function, because by their nature, they're divided by cosine, so you can't have cosine equal to 0. All right, so this one, as we found before, is D and E. You get there a little quicker using the tan secretary, but Santa Claus works out just fine too. In the end, we still get extraneous solutions.